hello everyone, and welcome to the Introduction to Python course. And in this course, what we're going to be doing is we're going to be covering the basic fundamentals of Python. Now in this first chapter, chapter 1, we're going to be talking about an introduction to computers and programming. So specifically, we're going to start by talking about just what computers are, what programming is. Next, after that, we'll go into sort of delineating what hardware is and what software is. Following that, we'll talk about how computers actually store data, so how they actually can store it in binary. Following that, we'll talk about how programs work, the ones that we're going to be writing. And then finally, we'll end with how we're going to use Python. So computers are just anything that we can program. So from your smartwatch to your tablet to any of that, those are all computers, and we design programs to tell them what to do. So programs are a set of instructions that a computer can perform or follow to perform a task. So any kind of software use, so Microsoft Office, your operating system, anything like that, those are all just programs that we build to tell the computer what to do. That makes us programmers. And in this class, we're going to learn to become programmers. We're going to be the ones who design, create, and test different computer programs, and we'll also be known as software developers. So if you've ever wanted a job doing software developer, a programmer position, this is the class for you because it'll teach you the basics of that. So to begin with, we'll first start with what hardware and software is. So hardware is just the physical, what you can touch, devices that actually make up a computer. So over here you'll see we have our floppy disk, we have our heat sink, we have our hard drive, optical drive, so on. The full board that holds everything is the motherboard. And some really major components of these is the CPU, or the central processing unit, which we'll talk about more in a second, main memory or RAM. We have secondary storage devices like your hard drive, that's where your actual data gets stored. And we have our input and output devices, which we use to communicate with the computer. That's such as your optical drive, your keyboard, and your monitor as well. So the first one we're going to really focus on is the central processing unit. The central processing unit, or the CPU as you'll hear it most likely called, is the brain of the computer. It's what actually runs the programs on the computer, and without it, you do not have a computer. You can't run software, you can't tell the computer what to do, because without a brain, how is it supposed to work? Now, microprocessors are just CPUs located on smaller chips. They're found on a whole bunch of other different devices that you'll see throughout your actual lifetime as a software developer or programmer. And again, those are just another version of a CPU or central processing unit. Main memory is the one that if you've ever wanted your computer to run faster, operate more efficiently, along with a better CPU, you always look for more main memory or more RAM. So this is where the reason this is because this is where your computer actually stores data for the programs it's actually running. So the more RAM you have, the more data it can store locally or closer to the CPU, because it's closer, the CPU can actually access it more quickly. However, the reason why we do not only ever use RAM is because it's volatile. Okay? If it's volatile, it means it's only temporary, and when we turn that computer off, everything in there is just lost. Now, moving on to, if we have that being stored and it's lost with RAM, secondary storage allows us to hold the data for long periods of time. So whenever you save a document to your computer, whenever you save a program to your computer, whenever you save a video, a game, anything like that, that's stored in your secondary storage. So we have different types of secondary storage, including our disk drive, which is a hard disk drive, or HDD, which just magnetically encodes the data onto spinning disks. Basically what it's doing is it's taking the data and it's putting little magnetic charges on a spinning disk, which tells the computer how to read the data. After that, we have our solid state drive, or SSD. Now the SSD, if you've ever seen any computers recently, these are an improvement to a hard disk drive, or HDD, because of the fact that they don't have any moving parts. So they're just faster. So in this case, we're actually the computer launches electrons at the solid state drive mesh, which tells the computer how to read the data. Followed by that, we also have flash memory, which we've all used as a USB drive. And we also have optical devices such as a CD, which has the data laser encoded onto a disk, which the computer reads as data. After this, we have our input and output devices. So first we have our input devices, in which case we use these devices for the computer to actually collect data from us or from other devices. So that's the input is us, and the input device is the one that collects it. So in this case, the types of input devices we have are things such as a keyboard, mouse, and touch screen. We also have scanners, cameras. We also have links between different computers, but we also have a USB drive and a disk drive. Now, a USB drive and a disk drive are very interesting because they also operate as output devices. Now, output is any kind of data that is produced by the computer for other people or devices. So whatever you see on your screen, whatever you print out via a printer, whatever you like, any kind of music you listen to, that's output. Okay. Now the output device is the one that actually formats and presents the output. So in this case, like a printer or something like that, and even a USB drive, like I said before, and a disk drive are also output devices. So we have all this hardware and this hardware. Now if we move on to software, this is what actually controls what the computer does. So we have the hardware, which actually runs the software. It's all the different parts needed to actually physically run the software. Now we actually have the software, and the software is broken into two different types. We have application software, which are the programs that make the computer useful for everyday tasks. So those are the ones that you most of the time actually run into. So things like word processing, email, games, web browsers, all of that sorts, those are application software. Now, the ones you don't see normally or you don't really think about all the time is what's called system software. This is the type of software or programs that we actually built to control and maintain the basic operations of a computer. So imagine something like, for a human, it would be like your immune system, it would be your heart. You never think about these things working, but for a computer, it's the same thing. We have our operating system, which controls all the hardware operations. We have utility programs, which enhance computer operations. And then we also have software development tools, which we're going to be using to create, modify, and test different software programs. So before we go any further, we can ask these questions. So the first one here is just, what is a program? So a program is a set of instructions that a computer follows to perform a task. After that, we can say, well, what is hardware? So hardware is the physical devices that make up a computer. If we wanted to list the 5 major components of a computer system, we have our CPU, we have RAM, we have secondary storage, which includes our hard drives, our solid-state drives, and such like that. We also have our input devices, and we have our output devices. So now if we ask the question of what part of the computer actually runs programs, that would be the CPU. Which part of the computer actually holds the data for long periods of time? That would be secondary storage. And what part of the computer collects data from these people and other devices? That's our input devices. And finally, the part of the computer that formats and presents data for people and other devices is our output devices. Moving on, we can ask the question, what do you call programs that perform a specialized task? So these are going to be our utility programs. Again, they're a subset of our system software, ones that we don't really think about. And what do we call word processing, spreadsheets, and email programs? We call them application software. So to really break this down, we can look at it like this. We can say we have software right here. So we have software. Excuse my bad handwriting here. Underneath of software, we have both application and system. So we have these two different types of software. So we have application and system software. Underneath of system, we also have utility programs. So you'll see this a lot throughout the course. We'll have different tree structures like this, but realistically in this case, remember that utility is a program. We have system software, we have application software, and the difference between the two is application software is the ones that we're going to use for everyday life, and system software is the one that's going to maintain the actual functions of the computer. Okay? So moving on, we can go on to actually how computers store data. So this is a huge thing in actual programming and just in general computer technology. And computers store data and a sequences of zeros and ones. So a byte is just enough memory to store a letter or small number, and it consists of 8 bits. Okay? And a bit is, imagine just you have a wall of light switches, and you have 8 light switches. Depending on how you have them, if you have some turned on and some turned off, that is how the computer learns and how it understands that this number is different from that number. So for instance, here on the screen, you'll see we have 2, and the binary for it, you'll see we have a little 0B in the front. That just means that the number following that, 0B, is binary. And in this case, the binary for 2 is just 1, 0. Okay? And for 22, we'll see it changes to a different number. Okay? So before we go any further, we can go further into this. So let's go ahead and clear what we have here. Use the lasso tool here to get rid of all of this stuff that we had before. Go ahead and just erase that there. That didn't work. Hold on 1 second. Come on. There we go. Grab all of that. Okay, so we have all that, and we'll just get rid of that. All right. So for binary, what we're going to do is we're going to say, if we have the number 10 in binary, we want to figure out what that is. So the way that binary works, it's to the power of 2. So it's a base 2. So if we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 spots. Again, so we have a byte, which is 8 bits. Each of these bits is some number of 2 to some power. So it's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. So what this is going to be, and you'll learn this as you program, it's going to be 1, 2, 4, 8, 16, 32, 64, and then 128. Okay? So what's going to happen here is if we want the number 10 right here, so we want the number 10, we're going to ask ourselves the question. We're going to say, we go from left to right, we go across, and we'll say, does 10 go into 128? No. 10 go into 64? No. Is 10 greater than 32? No. 16? No. 10 is greater than 8. So we'll mark a 1 here, and then we'll do, so we have a 1 here, and then we do 10 minus 8, which equals 2, like that. So now we have 2. Is 2 greater than 4? No. So now we start putting a 0 here. Is 2 greater than 2? No, but it is equal to it, so we'll put a 1 here, which is now then 2 minus 2, which now equals 0. So if we have this, we know that we're done. We'll put zeros in the rest of the spots. So the binary for 10 is 1, 0, 1, 0, just like that. So we go ahead and do another practice example here. Zoom back out here a little bit. Okay, just like that. And what we're going to do is we'll go ahead and erase what we had here. Make sure we choose the right eraser. Get rid of all this here. Okay, and again, we'll do it for the next one as well. So what we're going to do is let's take another number. Let's say we have 46. Okay, so we have the number 46 we want to do. Is 46 greater than 128? It's not, so let's put a 0 there. The leading zeros on this side, by the way, they do not actually matter, and I'll show you that in a second. Is 46 greater than 64? No. 46 is greater than 32, so we'll put a 1 here. Now we have 46 minus 32, which is going to equal, hold on, bear with me here. It's going to be 14 here, yep. So then we have 14, which is going to be, we have a 0 here for 16, because 14 is not greater than 16. We have 8 here, so it's a 1, because 14 is greater than 8 over here. So now we have 14 minus 8, and then we have 14 minus 8 here, which is another 6. So is 6 greater than 4? It is, so we'll put a 1 here. 6 minus 4 is a 2. And then 2 is greater than or equal to 2, so we'll put a 1 here and a 0 here, because when we do 2 minus 2, it's going to equal 0. So this gives us, for 46, we know that the binary is 1, 0, 1, 1, 1, 0. Okay? Now we can put as many leading zeros out here as we want. This right here does not actually matter, because they have no meaning because they're all off. The first value that has meaning is the first one from the left, and that shows that that's the value we're going to be working with. Okay? So this is how we're actually going to go from what's called base 10 or decimal, which is this one, to binary, which is the power of 2 over here. So if we go ahead and do this, we'll go ahead and we'll take this number now, and we're going to go the other way. So let's go, we'll erase all this here. This here. So we have our number right here, and that's 46. We have 1, 0, 1, 1, 1, 0. So what we're going to do is erase all the numbers we had before. Okay. Clean it up a little bit. All right, so now what we're going to want to do is to go back. What we're going to do is we're going to put this number that we have down here up here with all the powers of 2. So we'll have 0, 1, 1, 1, 0, 1. Now what we're going to do is wherever we see a 1, we're going to keep that number. So in this case, we have a 1 here, so we'll keep 32. We have a 0, so we're going to get rid of 16. We have our 8, which has a 1, so we can keep that. We have a 1 and a 4, so we'll keep that. A 2 and a 1, so we'll keep that. But 1 and 0 do not have 1, so we'll erase that there. So now what we do is we're going to go ahead and add all these numbers up. So we're going to do 32 plus 8 plus 4 plus 2. So if we add all those up, we have 32 plus 8, which is 40, plus 4 plus 2, which is 46. So that is how you're going to go the other way. Okay? So again, binary is a very powerful system because it allows the computer to simplify the numbers that we're working with into a way that the computer can easily understand it. Okay, so again, we talked about this just a second ago. If we have the number 0, all the bits are off. If we have the number 255 with 8 bits, all the numbers are on. So for instance, if we go back to our example here, and we erase what we have here, so we'll go ahead and erase all these. Go ahead and erase this, put it back to the way it was. And we put those numbers back, so we have our 16 here, our 8 here, 4, 2, and 1. If you add all these up, so if you do 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you're going to equal out to 255. That is the maximum number that you can store with all ones. So this is 1, 1, 1, 1, 1, 1, 1, and 1. So this is 255. You know it's 255 because if you did 2 to the 8, like that, the next number would be 256. Okay? So this number that is here, this 255, with all the bits on up here, so 2 to the 0, all the way up to the 2 to the 7, those are all on. So we have 8 bits turned on, that's 255. If we wanted to do 256, we'd have to add an extra bit, turn this on, and every other bits, all of these ones here, will be zeros. So we take all those out, and we put zeros, just like this. And this is 256. So if you don't know what the maximum value for those bits is, think about the next power of 2 and subtract 1. So that's a 0 there, sorry about that. So again, what we have is we have 256 minus 1, which is 255. So if we turned on all of these other bits on this far side, all 8 on the right side there, we would get 255, and if we turn them all off and turn the next bit on, we'll have 256. The reason this is because binary goes, if we have 0, 0, 0, 0, so 0, 0, 0, 1 second, there we go. If we do the next number, it would be 0, 0, 1, then it goes 0, 1, 0, 0, 1, 1, and it goes 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. So as you grow, you'll see we had them all off first. We turn the furthest right one over. So this is 0. This is equal to 0. This is equal to 1, because we only have 1, so that's 2 to the 0 is 1, so we have 1. We have 1, 0, which is equal to 2. We have 1, 1, which is equal to 3. 1, 0, 0, which is equal to 4. 1, 0, 1 is equal to 5. 1, 1, 0 is equal to 6. And then 1, 1, 1 is equal to 7. And you know this because if we have the fourth bit on right here for 8, so this guy right here, we have that turned on, all the other ones are off, so now we have 1, 0, 0, 0. So if 8 minus 1 is 7, so we have the 3 bits on, the 8 tells us we have 3 bits on, it's now 7. Okay? So binary is a little bit confusing, but over time you'll get it, and if you're working with a lot of computer architecture systems, you will use it. Otherwise, you won't come across it too often, but it's important to notice it. Okay? So let's go ahead and try this. So we were just going over it a little bit, so we don't have to worry about that right now. But again, keep in mind that when we were trying it out, we had the different numbers, and again, we build up binary from right to left, and each of the different ones is a different power of 2. So we have 2 to 0 on the far right, all the way up to 2 to however many spots are over on the left. All right, so moving on with binary now. When we're storing characters, all the data that's stored in a computer has to be stored as binary numbers, which means we can't just store text in a computer. So we need some way to understand and store text in a computer. So the way that we're going to do that is we're going to convert characters to numeric codes. So imagine that if we had, so let's go ahead and get rid of this, but imagine if we had Imagine that if we're trying to store the letter A, so we'll say A here. All right. So if we have A here, we'll say A, and we'll say that's equal to 1, and B is equal to 2, and C is equal to 3. So in this case, what we're doing is we're storing all the letters as numeric codes. The computer does this, but again, it doesn't use 1, 2, and 3. It uses binary. Okay? So what that's doing is it's saying that we take some number of bits, and we're going to use those to store the characters binary. Now, there's two different ways we can do this. We can use ASCII or Unicode. Now, ASCII is limited to only 128 characters, and it's perfect for the English language. However, the world goes beyond English language. We have different languages. We have Chinese, we have Russian. They don't use the same characters as we do. Okay? So they don't use the Germanic alphabet. And with that, we actually want to make sure we can include all the data from all the different countries so we can communicate well through the computer system. So to do this, we expand ASCII. So we expand it by using what's called Unicode, which is compatible with ASCII. So instead of using only the 1 byte or 8 bits for each character, we're going to expand it out with more bytes as well. So instead of 1 byte, now we have 2 or 3 or 4. And that's how we're going to use Unicode to actually work and represent the characters of other languages. Okay? So now on top of that, we also have other advanced number storage and formats. So you don't have to worry too much about this in this class, but it's good to know they exist. So when we're working with computers, we know that we can store the number 1, 10, 15, 20 using binary. However, when we're dealing with negative numbers or floating point numbers, or should I say decimal numbers that you're probably more accustomed to that name, we need a different way, because you can't store a decimal point number like 3.14 in the computer just by itself. You can't really do that. So what we use is we use what's called the Single Precision IEEE 754 floating point standard, which you can see here on the left. So what that does is it says, we'll take the first bit, we have 32 bits here, and we're going to take the first bit and say, if that's a 1, it's negative. If it's a 0, it's positive. It uses that 1 bit to determine whether it's positive or negative. After that, it's going to use the next 8 bits to determine the actual scale or magnitude of that number. So you can imagine that if it's something like 1,000, those exponent bits will be higher than if it's the number like 3.14. Okay, so that's how that's going to work. It's going to use those 8 bits to represent the actual magnitude of the number. Now after that, it's going to use what's called the mantissa bits, the rest of them, to actually keep the precision. So when we have 3.14159, we want to make sure we keep the 14159 because we want to make sure we're out to that much precision. So when you're working with any kind of scientific data, or if you're working with any kind of statistics, you want to make sure you're accurate. So the mantissa bits allow us to keep that precision, and the exponent bits allow us to get the magnitude. Putting those back together, the computer is able to reconstruct the floating point number we have to a pretty good, not perfect, but pretty good representation. So there is some error that occurs from using floating point numbers or decimal or the floating point standard, but it is an acceptable error because it is so far out there. It's like we're looking at 0.000 all the way out to a certain point, but at that point we know that it's going to be an error and we're okay. But it doesn't mess with really too much, if any, kind of scientific representations. Now, moving on to negative numbers, we also need to keep track of that. So now we could do something similar to the single precision IEEE 754 floating point standard, and we do. So in the floating point standard, we use the farthest left bit of the 32 bits. So if it's a 1, if it's one side, it's one way. If it's a 0, it's the other way, and positive or negative. Okay. So 2's complement does the same thing. So you'll see here on the right, if we have 0 and then 1, 1, 1, we have 7. If we have 0, 1, 1, 0, we have positive 6. But if we want negative 7 or any negative number, we're going to change that first bit, the farthest left bit, to a 1. So we'll turn it 1, which signifies to the computer that that is a negative number. Now, what it's going to do is it's going to go the opposite way. So if we have 1, 1, 1, 1, we know that it's just negative 1. It's on the opposite side. All the way down to negative 8, which is just 1, 0, 0, 0. And then we have negative 8. Now it's a little bit confusing, but again, for this class, you don't have to worry too much about the 2's complement. Just know that it exists, just like how you know the floating point standard exists. Now you will be using floating point numbers in this class, but you will not have to worry about this actual representation. Okay? So lastly, we also have other types of data. We have digital data. So digital data is just any kind of data that's stored on the device. So if you hear about any kind of digital data structures, digital anything, that just means computers. So when we're talking about images, images are comprised of different pixels. So when we actually store an image on the computer, each pixel is it's usually an RGB value, and it's comprised of 3 numbers that tell the computer how much red, how much blue, and how much green, so RGB, to actually use to color that pixel. And the image is comprised of thousands of pixels, which gives it a very good quality, and the higher the number of pixels you have, the better quality you have. Music is in a similar way, and it's composed of sections called samples, and each of those sections is converted to, or each of the samples is converted to a binary number. That's how we store them. So when you're listening to your MP3s, those sections are being played out of those samples that are being stored as binary numbers. So a little bit of a checkpoint here. If we ask the question, how much memory is needed to store a letter or small number? The answer is going to be a byte or 8 bits. Now we're talking right now about just a letter or small number. We're talking about an English letter or small number. So again, a byte or a bit goes up to from 0 to 255. So that's enough to store any kind of small number as well as store a letter. Now we ask the question, what numbering system uses all of its values as zeros and ones? That's the binary system. We ask the question, what is the purpose of ASCII? Because remember, we have 2. ASCII is used to represent English letters, numbers, and symbols. And if we want to encode the characters of many languages, we're going to use what's called Unicode. Okay? All right, so moving on, we can ask ourselves, okay, so we now know how the computer stores data. We now know how hardware and software work. But now we ask ourselves, well, how does a program actually work? So we build the program, and CPUs are designed to perform single operations on pieces of data, which means that it's going to read data, it can add or subtract or multiply, divide numbers, and then it's going to output something, okay? So how this is going to work is it actually must perform many operations, because we don't want to just do a single add, a single subtract, or something like that. It has to do many operations in a row for us to get something that we want. Okay, so a CPU is going to follow a standard cycle. It's going to fetch the next instruction from memory. It's going to decode that instruction into determining what operation it needs to do, and then it's going to execute it. After it does this, it's going to go again. Now, all of these instructions are actually just stored in RAM, and they're just copied from RAM to the computer or the CPU each time that we need to execute it. Okay? So as you see here, if we have an instruction, so again, instructions are written in binary, that binary is passed to the CPU, where it decodes and it figures out what does it need to do. It then executes it, goes back to RAM, and gets that second line. And then gets to the third line, and the fourth line in RAM, and so forth. All right, so now we know that it's stored in binary. And the thing is, there's many different ways that we can talk to a computer. We can program a computer, we can interact with a computer. So the lowest level that we have is what's called machine language, and we don't really want to work with that. If we had an actual spectrum here, so if we come over here, let's go ahead and erase these guys out. If we were to draw a line, a standard complexity line, so if we were to come over here and say we have a straight line here, and on the far side over here we have more readable, and then over here we have more computer readable. We have on the right side what we want, and the left side what the computer wants. Now the computer wants everything over here. It wants everything in binary / machine language. So the machine language is what the computer is going to use. It's all in binary, and that's what the computer uses to determine the next instruction. So we don't really want to use that. So we have different options that we can use to translate, if you will, what we want to do into the language the computer wants. So the most basic one, or the most low-level language we can use, is called the assembly language. And it uses short mnemonic words for instructions instead of using binary numbers like machine language. Okay? The assembler is what's going to take that assembly language and it's basically a translator for us. It's going to translate that assembly language we give it into a machine language or binary for the execution by the CPU. So assembly language would pretty much go right here. So it's not really human readable, but it's better than binary. So we'll say assembly right here. So assembly language. Okay, so we have our assembly language right there. Okay? So we can do better though. Okay, so we have both different types of languages. We already talked about the assembly language, which is a low-level language, but we also have high-level languages. Now these are the ones we want to work with. They're the ones that are very easy for us to read, easy for us to work in, and we don't need to know how different CPUs work to write any kind of actual programs for them. Because if we have different CPUs, for instance, if you look on the market, you'll see we have Intel CPUs, we have AMD CPUs. They have different instruction sets or different machine language instruction sets. We don't want to have to figure that out. So what we can use is we can use high-level languages such as Python, C or C#. Now in this class we're going to talk about Python, but in the future classes in this major you're going to be talking about C# as well. They're just more intuitive to understand. Okay? So these high-level languages are built off of what's called keyword operators and syntax. Now keywords are just predefined words we use to write a program in a high-level language. So you'll see in Python we have keywords for things like def, so def is a keyword. We have other ones as well that we'll talk about. But these are ones like def, if, while. Those are keywords that we cannot use for our own variables, which we'll talk about later. But they're just pre-programmed into the actual programming language that tell the computer what we want it to do. Next, we have our operators, which are just symbols used to perform operations on the data. So again, examples of this would just be math operators. So you can't use the plus, minus, the star on your keyboard, the slash for divide. Those all are just operators. So you cannot use them for naming anything in your programs as well because they are reserved characters. Now, these keywords and operators are all comprised back to a list or a set of rules called syntax. So if you ever hear somebody say you have a syntax error, it means you violated the rules when writing a program. Now, when we write programs, each line of our code that we're going to write is called a statement. So it is a single instruction. So when we say A equals 2 plus 2, that is a statement. That is saying we want the computer to take the value of 2 plus 2, which is 4, and say the variable A is equal to that. So now if we ever look at A later, it's going to be equal to 4. Okay? So now before we can actually get into actually building our programs, we need to understand how they are compiled or interpreted. Now there's two different ways. The compiler is the one that is going to be faster because it's compiled. However, it translates the actual program into machine language that's able to actually be executed by the CPU at any time. You only need to compile these one time, and then you can run it by the CPU anytime. Now the pros of that is that it's faster because you compiled it one time. The cons of that, though, is the fact that now, if you want to make a change, you have to change it, save it, and then recompile it. Next, instead, what we're going to use in this class is what's called an interpreter, because Python is an interpreted language. Now, what this means is when you run the Python program, the computer doesn't try to figure out the machine code of everything at one go. Instead, what it does is it says, give me the first line at the top of your program. So it starts from top to bottom. It gets the first line, reads it, translates it to machine language, and runs it in the computer. And every single line after that is going to be read as machine language, translated into whatever language, not read as machine language. It's going to be read as your Python language, translated to machine language, given to the CPU, and executed. Every line. Now, the problem with that is that is slower. However, it may be slower, but it's more user-friendly, because now if you want to make a change, instead of having to recompile it, you just make a change to your program, save, and rerun your program. Also, if your program breaks at any point, you know exactly where it broke, because now you can see, oh, it broke on line 10. I need to go to line 10 and fix it. It's very easy to see. Now, whatever program you're writing for, whether it's C, C#, Java, Python, doesn't matter, the code that you write with all the statements that we talked about before are going to be your source code. And again, like I said earlier, if you have an error called a syntax error when you run your code, it means that you have violated the rules of that programming language which means that the computer cannot translate it until you fix that issue. So if you put something in the wrong spot, if you don't have something indented correctly, because indentation does matter in Python, we'll talk about that later, all of that will make the code unreadable by the computer, and therefore you cannot convert it from your programming language to machine language to give it to the CPU. So here's an example of this. So if we have Python, because again, we're going to be using an interpreter, not a compiler. We're using an interpreter because Python is an interpreted language. If we want to say the word print hello earthling, what it's going to do is it's going to take and put those words in the quotes to your screen. So it's going to print to your screen hello earthling. When we run that code, that line will be read, that statement will be read by the Python interpreter. It'll be translated to, okay, the CPU needs this instruction, passes it to the CPU, it'll run that command, printing the words hello earthling to the screen, and it will go back to the next line. It'll continue to repeat this process until your program is over. Now, just a little bit of a checkpoint here. If we ask the question, how does a CPU understand instructions written in what language? What we're asking is, it understands it in machine language. Okay, so I know I've sort of read that question a little bit weird, but all I'm asking is, if a CPU has a language, or if we talk about that language, what language does it understand it in? So it's machine language. So if we go back to our diagram, we have machine language on the far left, assembly there, and if we come over to more readable, over here, let's say right here, we have things like Python, and if we were to put C somewhere, Python would be here, maybe C would be right here, C# maybe right here. So we have our high-level languages there, we have our assembly language, which is a low-level language in the middle, and we have binary or machine language that the computer reads. Next, we'll ask the question, programs are copied into what memory each time a CPU executes it? So again, remember, we have our CPU, it needs the instructions. Your instruction is your program. It's copied into RAM, or main memory. We ask the question, what is assembly language? We talked about this before. Again, assembly language allows programmers to use short word instructions, and those are then converted into machine language. So instead of having to work with binary, you just work with assembly language. Again, we do not want to work with that. That is a nice middle ground if we need to go down there. Most of the time you won't need to, but if you do, you'll use assembly language. You won't write in machine language. Okay. If we ask the type of programming language that allows you to create powerful and complex programs without knowing how CPUs work, those are called our high-level programming languages. Again, that's things like Python, C, C#, and so on. If we ask what is the set of language rules you must follow when writing a program, that is called syntax. Again, remember that if you break that rule with the syntax, you get a syntax error. And you have to fix it before the computer can convert your code to something that the computer can read. Next, we'll ask the question, what is a program that translates and executes instructions of high-level programs? It's an interpreter. Note here it says program that translates and executes instructions of high-level program. If it said program that compiles or translates and saves for later execution, that's compiled. In this case, we're saying a program that translates and executes. So it's both at the same time. That's an interpreter or an interpreted programming language. Okay? So now if we go on finally to actually using Python. To do this, we must first install Python. So in this class, what we're going to be doing is we're going to be using what's called PyCharm that you see here. So this is PyCharm, and it's a very basic, just super streamlined Python IDE, or interactive development environment. When you install PyCharm, you will see that you will have this screen here. It'll give you just a very basic introduction here. Now you may ask the question, well, how do I get to PyCharm? Okay, so the first thing you'll need to do is you need to install Python. So if we go over here to Firefox, let that open up real quick. Might take a second. And we first go to python.org. If you go to python.org, it'll first pull up, and what you're going to want to do is you're going to want to go to Downloads, and you either go to 3.11 or 3.10, whatever the most recent one is, you click that, and it will download it for you. If you don't want to do that, you can click Downloads here, and you'll find the orangish yellow button here. I guess it's more yellow, but this yellow button, you click that and it will download Python for your computer. You step through the installer, and now you have Python installed. That is the interpreter. Now, to actually code in Python, what we need to do is we need to install PyCharm. We do Python first, PyCharm second. We go and type in PyCharm, hit enter, and we're going to do the Python IDE here. We'll go to download, and then from there we're going to do the community, not professional community. I'm on a Mac, so I have a .dmg here. For you, you'll see it should come up with what you want. You click download here, run through the install options, and you'll be set. So after we have both of those, we have now installed Python. Now Python, when you install it, comes with an interactive mode and a script mode. The interactive mode allows you to enter statements on the keyboard, and the script mode allows you to save the statements in Python scripts. We won't use interactive mode, but if you wanted to use interactive mode, you would open your terminal after you've installed Python and type in either Python or Python 3. Here you'll see I have Python 3.7 or 3.10.7 here. If at this point, if I do print with the parenthesis, I'm going to say quote, hello world, end quote, end parenthesis, and hit enter, it'll print what I told it to the actual screen. If you want to get out of this, you type in exit, all lowercase, with open and close parenthesis after that. So those are the first two lines we're going to have to learn in Python. We have our print statement, which is one you're going to be using all the time, and if we have exit here, which closes your program. Okay? So that is called the script mode. That's called the interactive mode. Script mode is basically what we have here with PyCharm, where we can type multiple commands. So here you'll see we have our print statement here. And this is where we'll actually start typing our actual Python commands. And then we can save them and run them up here with this run button here. Or you can go to run like this. And that's how we can actually run it after saving it. Script mode is better just because of the fact that you can save your commands. You don't have to type them because interactive mode will not save the commands you type. Okay? So again, we talked about interactive mode. Interactive mode is really good for if you just want to test something new with Python. Cool, you can do that. If you're trying to type a new command, just see what happens. You can use interactive mode. But I would prefer you actually use script mode here. So again, with script mode, you'll see we talk first about we save a set of Python statements in a file. So if we come over here to Python, and let's just say we get rid of all this stuff, you can go ahead and get rid of that. And if we just do print hello, and then we do print world. If I save those with Control S, or you can do file, and you can do save, or save as, either way. We'll just save as main.py. After you save that, it already exists, so it's okay. We save that, and we go to run at the top, and we hit run again. We click main. That's the file that we're on with main right here. And you'll see it'll print hello and world on two different lines, because we have print and print. So we've saved the Python statements in that file. You notice here that again it ends in .py, so it's main.py. If your file does not end in .py, the computer will not recognize it as a Python file, and the interpreter will not run that code. Afterwards, we can either run it like we have here, or if we open up a terminal down here, see if I can find it. See, I can actually just go to this location as well, but if I wanted to, I can go into the actual terminal, cd PyCharm, go to /PyCharm, cd chapter 2. So this is just standard Linux commands you'll learn later, but I'm just trying to show you that if I do Python 3 main.py, you won't have to do this. Again, just use PyCharm for this, but I'm just showing you this for your sake. If I run this, it'll now say hello and world, just like it did down here. Again, do not use the terminal unless you really want to try it out, but again, don't try to break your computer. It's easier just to go through PyCharm. So either way, you can, with the script mode, you can run it through PyCharm, you can run it through your terminal. All of those, though, you can work with, and if you save it, you run it, and you can run it again later. Interactive mode, you cannot save it. So there is also something called the idle programming environment. We're not going to use it in this class, but it's called the Integrated Development Program for Python, and it comes pre-packaged with Python. Again, we're not going to use it mostly because of the fact that it's it's more low level. If you want to take a look at it, go ahead. It runs in interactive mode, and it automatically comes pre-installed with the Python language. Just know that idle exists. Okay? So in summary for this chapter, we've covered what the main components of the computer system are, the types of software, how data is stored in a computer, the basic CPU operations and what machine language is. We talked about the fetch, decode, and execute CPU cycle. We've also talked about complex languages and their translation to machine code, and how to install Python and the Python's interpreter modes. Okay? So in the future classes, we'll actually start diving into actually programming in Python, but this will cover where we're currently at, really just the fundamentals. And again, in the next video, in the next chapter of chapter 2, we'll start actually programming in Python. Thank you.